earlier we looked at how split iterator performance affected parallel streams. We saw that split iterators for array lists split more evenly and efficiently than split iterators for linked lists. Now we're going to look at the other end of the stream, which is collector performance. And we're going to talk about the difference in performance for concurrent and non-concurrent collectors. And we'll also talk about the difference related to the type of data that you're merging together by the collector. And once again, you can find this in the EX14 folder, and we'll look at the source code in a second. So as with split iterators, concurrent and non-concurrent collectors perform differently when used in parallel and sequential streams on different input sizes for different data types. And in this particular case, we're going to see that there's going to be a couple of different things we're going to look at. We're going to compare a version that uses a hash set as the data structure we're going to be combining. And as you'll see, the hash set's going to have both sequential and parallel implementations. And then we're going to compare and contrast those to something that is a concurrent hash set. And as before, when you have a small number of input elements, the performance of all these things is roughly the same. But when you start having a larger number of elements that you're dealing with here, when we get up to 883,000 or whatnot, you can see it makes a big difference, or a bigger difference. So first of all, one of the things to note here is that parallel and sequential don't really matter when results are small. In fact, the parallel version is actually a little bit slower. And that's because the input's so small, and setting up the apparatus for parallel processing just takes some time, as we've discussed before. When we get down to the large number of elements to process, you'll see that both of the parallel versions perform substantially better than both of the sequential versions. And you'll also notice that the one that uses the concurrent collector performs much better than the one that uses the non-concurrent collector. And that's because the concurrent collector is merging everything into a single data structure using a concurrent hash set, which is basically a little wrapper around concurrent hash map, whereas the non-concurrent version is actually having to merge together hash sets. And so that takes longer to run. So we'll go ahead and take a quick look at the source code to illustrate these things. It's really kind of interesting and very, very instructive. So we're back in our EX14 example again. Remember, we've got the works of Shakespeare here. What we're going to look at here is the run collector tests code. And if we come down here, you'll see here's run collector test. Run collector test is much the same as before. For the split iterator test, we iterate 1,000, 10,000, 100,000, and up to 1,000,000 words in the works of Shakespeare. In this particular case, we're just going to focus on array words because we've already discerned that linked list implementation performance sucks in comparison. And then we're going to go ahead and run a couple of different tests a couple different ways. So we're going to run one test called time stream collect to set. So this is going to collect to a hash set, and we're going to do it both sequentially, i.e. parallel is false, and in parallel, i.e. parallel is true. So that's one test we're going to do. And then another test we're going to do is time stream collect to concurrent set. And this is using a concurrent collector. And again, we'll do a sequential version of that and a parallel version of that. So let's go ahead and find that code down here. And here we can see run collector tests. Whoops, sorry. That's what we want. We want that guy. All right, so let's go down here. So here is time stream collect to set. You can see it takes Boolean flag to indicate whether to run it in parallel or sequentially. It takes the list of words, which we know is an array list. And what it does is it goes ahead and iterates again for some number of times just to do something interesting and make the results meaningful. The first thing it does is it creates a stream from the list. And then if we're running in parallel, we turn it into a parallel stream. If it's a sequential run, we don't turn it into parallel, so it'll be a sequential stream. This illustrates how you can dynamically turn on parallel streams by some kind of flag check conditionally. Then what we do is we take that stream and we go ahead and essentially map each string to lowercase. Not the most interesting thing to do, but it's kind of the inverse of mapping everything to uppercase, much as we've seen before. And what we're going to do then is we're going to go ahead and collect the results. So remember, all this stuff is either running sequentially or it's running in parallel. And then we're going to collect the results of the uppercase into a hash set. And what will happen here is if we're doing the sequential version, then obviously it'll all run in one thread. If we're doing the parallel stream version, then for each of the chunks, we're going to have different intermediate hash sets that are used to collect the data into. And then each of those hash sets will be joined as the collector works, and we end up with one single joined result. And so, or merged is probably a better word than joined. And so as a result, for the parallel version using a hash set, there's a fair amount of overhead because you have to merge the hash sets back together again. In contrast, let's take a look at this implementation. This is the same logic, except this time we're going to use a concurrent collector, not a non-concurrent collector. So almost everything looks identical. We have a certain number of iterations. We either do things sequentially or in parallel. The difference here is that this implementation uses the concurrent hash set collector as opposed to the sequential non-concurrent hash set collector. And the concurrent hash set collector, if you were to look internally, uses a concurrent hash map, which is super duper optimized to run well in multi-threaded programs. And so there's only a single mutable result container for this collector as opposed to one for each chunk that gets merged successively to a single result, a single merged result with the earlier version. So as a consequence, all those threads running in parallel, when they do the collect, they simply collect into the one and only mutable result container, which is a concurrent hash set. And you can see when you look at the results that this version performs much better when we have a large number of elements to process. So as you can see here, just to reiterate this point, for small inputs, they're about the same. In fact, the parallel version is slower because there's more overhead for parallelism with input that's small. That's the whole n times q model discussion. But then as we get a larger number of elements to process and collect, the concurrent hash set version is much faster than the hash set version that's non-concurrent. And of course, both of those are much faster than the sequential versions because they're taking advantage of parallelism. Okay, so that's just kind of illustrating the merging dimension here.